Picture this. You're teaching a puppy a brand new trick. Every single time the little guy does something wrong, you gently correct him. And over time, through many, many corrections, he gradually figures it out and gets better. Well, machine learning works exactly the same way. We start with a mathematical model that makes predictions, it inevitably makes mistakes, and we just correct it repeatedly until it gets good. Exactly. That entire process of continuously correcting the model is what we call optimization. And the ultimate mathematical engine driving almost all modern AI? It's an algorithm called gradient descent. Let's dive in and figure out exactly how this works together. To correct our model, we first need to know how badly it actually messed up. And this brings us to the loss function. The loss function? It measures how wrong our model's prediction is for just one single example. Think of it like the penalty for missing a single question on a pop quiz. Answer perfectly, the loss is 0. Completely off base, the loss is high. Let's put some real numbers to that. Say we're predicting house prices. We'd use mean squared error. The formula works like this. We take the actual price minus the predicted price, and we square the result. Now, why do we square it? Well, if our prediction is too high by 20,000 on one house and then too low by 20,000 on the next, those errors would just cancel out to 0 if we just added them up. Squaring makes all the errors positive. But far more importantly, it severely punishes the model for massive mistakes. Being off by 100 gives an error of 10,000, but being off by 1,000 gives a squared error of 1 million. The model quickly learns to avoid those catastrophic mistakes at all costs. But what if we aren't predicting a number, and instead we're looking at a category, like trying to figure out whether an email is spam or not? For that, we use cross-entropy loss. The math here uses a logarithm function, which has this really beautiful property. If the model predicts there's a 95% chance an email is spam, and it actually is spam, the penalty is tiny. But if the model is highly confident, say 95% sure it's just a normal message, and it turns out to be spam, the logarithm creates a massive penalty. It forces the model to learn that being highly confident but completely wrong is literally the absolute worst thing it can do. Right, so we have these penalties for individual predictions, but we really need to look at the big picture. That's the difference between the loss function and the cost function. If the loss is how wrong you are on one single quiz question, the cost function is your average score across the entire exam. And our ultimate goal in training any AI is to minimize that overall cost. We want the absolute lowest possible average error across all our data.
The Valley, Understanding Gradients.
Picture yourself completely blindfolded, dropped entirely alone, somewhere in a vast, jagged landscape. Your only goal is to survive by finding the absolute lowest point, the bottom of the valley. But you can't see a thing. So what do? You feel the ground under your boots. You sense exactly which direction slopes downward. You carefully take one single step downhill. And then you do it again. You repeat this over and over until the ground finally flattens out. This is exactly how our AI model finds the lowest error. Let's translate that hiker's slope into actual math. That slope is a vector of partial derivatives called the gradient. The gradient. It tells us if we change our model's weight by a tiny microscopic amount, does the cost go up or down? Looking at our numbers here, if our weight is at 3, our calculated gradient is a positive 6. The slope is going up, so to go downhill, we must move our weight in the negative direction. Now, if our weight is at -2, the gradient is -4. The slope goes down, so we have to move our weight in the positive direction to find the bottom. And if the gradient is exactly 0, we are perfectly flat. We've hit the absolute minimum error. So how do we actually take that physical step in the math? Here's the absolute most important formula in all of optimization. New weight equals old weight minus open parentheses learning rate times gradient close parentheses. I want to draw all of our attention right to that minus sign. It's the entire secret. Because the gradient always points uphill, we absolutely must subtract it to force the model the exact opposite way, pushing it downhill. Let's trace these steps towards 0 using actual numbers. We start up high at a weight of 4. We calculate our gradient, apply our update rule, and take a step. Our new weight is 3.2. We recalculate and take another step. Now it's 2.56. Another step, and it drops to 2.048. Notice what's happening here. As the slope flattens out near the bottom of the valley, the gradient shrinks and our steps naturally slow down so we don't accidentally overshoot our target. Tuning the learning rate. This dictates exactly how wide of a stance our blindfolded hiker takes with every single step. And it is a classic Goldilocks situation. If our learning rate is too large, our hiker is taking massive, wild leaps. They'll bounce back and forth across the valley walls in total chaos, maybe even climbing higher. But if the step size is too small, the hiker takes these millimeter-wide shuffles. It'll take an absolute eternity to reach the bottom, which in deep learning means days or weeks of agonizing, wasted GPU processing time. We have to tune it to be just right so the model converges nice and smoothly.
Now, to make those steps even more efficient, we actually have 3 different ways to calculate our slope. We could use batch gradient descent, which looks at our entire data set before taking a single step. It is incredibly stable, but painfully slow. Or we could swing the other way and use stochastic gradient descent, which looks at just one random example per step. That's lightning fast, but the path gets very chaotic and zigzaggy. So what do we actually use in the real world? Mini batch gradient descent. We look at a small chunk of data, say 64 examples at a time. It gives us the stability of the full batch and the speed of the single example. It's the industry standard for sure, because it perfectly utilizes modern hardware.
And we don't just stop there. We use advanced optimizers to supercharge this process. Imagine giving our hiker a really heavy backpack. That is momentum. It remembers the previous direction and builds up serious speed when heading down a long, consistent slope. And then we have Atom. Atom is brilliant because it combines that momentum with a custom adaptive learning rate for every single weight. If a weight hasn't changed much, Atom gives it a bigger learning rate boost. But if it's bouncing around wildly, Atom dynamically shrinks the steps to calm it down. Hold on, let me push back on that for a second, because all of this assumes a perfect, smooth, bowl-shaped valley. What happens if our blindfolded hiker walks down a slope and gets completely stuck in a random ditch halfway up the mountain? That ditch is what we call a local minimum. The model thinks it's at the absolute bottom, but it's really, really not. Or what if they hit a completely flat plateau, a saddle point, where there is literally no slope at all to guide them? These are the brutal, real-world challenges data scientists face every day. And it's exactly why those advanced optimizers like Atom and the built-in noise from mini-batch calculations are so vital. They literally jostle the hiker out of the ditches so they can keep searching for the true valley floor. The complete training loop. Let's put the whole puzzle together. Here is how every single cycle works. 1. Make prediction. The model takes a guess based on its current weights. 2. Measure error. We use our loss function to calculate exactly how wrong that guess was. 3. Figure out direction. We calculate the gradient to feel which way the slope is pointing uphill. 4. Go opposite direction. We apply our update rule, subtracting the gradient to force the error down. And 5. Repeat. We do this thousands or even millions of times. To wrap this all up, if we strip away every single piece of technical jargon, here is the exact journey we just took. We find the error on one example. We calculate the average error on all examples. We find the slope of the cost. We determine our step size. And finally, we move our weights opposite the slope until we hit the bottom. At its absolute core, we're just guessing, seeing how bad the guess was, and stepping the other way until we get it right. But it leaves us with a massive question. If gradient descent is just walking downhill, how does AI ever learn to navigate a landscape that is constantly shifting in real time? Keep stepping downhill, and we'll see you next time.